Good morning, good morning, everyone. Let's get started. So, in the previous classes, we were talking about the capacity region of the two-user discrete memoryless multiple access channel. And in the last class, I gave the converse proof, and before that, we saw the achievability. So, there are different ways of representing the achievability region. One is as the convex closure of a number of pentagons, where each pentagon is described using the following mutual information terms. So the achievable rate region, the capacity region, looks something like this, right? Or another way, a better and sometimes more convenient description is the following. So the capacity region can also be described as follows. So it is a set of all R1, R2 satisfying so R1 is less than or equal to the mutual information between X1 and Y given X2 and Q. R2 is less than or equal to the mutual information between X2 and Y given X1 and Q, and R1 plus R2 is less than or equal to the mutual information between X1, X2 and Y given Q, right? And this for all, so or should say for some joint distribution. So Py given X1, X2 is of course specified by the channel, right? So that is not under our control anymore. But the only things under control are the distributions on X1, X2, and Q. And this is taken over all possible distributions which satisfy the following property. So for some PQ and conditioned on Q, X1 and X2 are independent of each other, right? Because after all, the encoding is done independently, the messages are independent. But Q is the time sharing random variable, so it's some kind of shared information. So P X1 given Q, X1 given Q times P X2 given Q, X2 given Q. All right, so you look at all possible distributions of this form, and then each collection of PMFs of this form gives you a set of mutual information terms. So the set of all rate pairs which satisfy these, they correspond to the capacity region. Right. And in the previous class, we saw that all that this PQ of Q has to satisfy is that it is over some finite alphabet. Right? There was no condition or there was no bound on the cardinality of Q. But in fact, what you can show is that Q can be taken to be just binary. So this is a consequence of a result in convexity theory, and we won't get into this. So it's a consequence of what is called the Fenchel-Eggleston Carathéodory theorem, and you can take a look at it in the textbook. Right? Even the textbook, I believe, doesn't give a proof of the theorem itself, but it suffices to know that as long as you have a convex set of this form, as long as it's a connected compact convex set, you can represent any point in this set as a convex combination of 2 points, right? And so Q can be taken to be binary. So this PQ can be taken to be a Bernoulli random variable, or Q can be taken to be a Bernoulli random variable, and X and X1 and X2 are of course specified. right? So that makes our job easier in trying to search for the optimal rate pair, right? So, or to find the capacity region. So now your search space consists of distributions over the binary alphabet and conditional distributions corresponding to the input alphabets x1 and x2. Right. So in this class and maybe the next, we'll see a couple of examples of some channels. We'll start with the Gaussian MAC, and maybe we'll see a couple of simple binary multiple access channels, and try to see what the capacity region looks like, what regions are achievable using different schemes, and so on. All right. But before that, are there any questions? Any questions? So although here we've looked at all possible input distributions, so the same results can be extended to the case when you have input cost constraints, right? So for example, if you have some kind of a power constraint at each transmitter, then then in fact it turns out that you have an identical capacity region, except that the class of distributions over which you over which you find this rate region is a little more constrained. So you can't look at all possible px1 given q and px2 given q. You also want to ensure that the expectation over px1 of whatever the cost constraint is, beta of x1 should be less than or equal to uh, whatever uh, b or something like that, right? So so whenever you have, suppose you have a cost constraint that beta of x1 should be less than or equal to b, then you optimize, or you try to find all of these mutual informations, or you compute all of these terms under the constraint that px1 satisfies beta of x1 less than or equal to b in expectation. So this way, let's see an example. All right, so let us focus on the two-user Gaussian MAC. So once again, the two-user Gaussian MAC is the following. So you have two transmitters and one receiver. Transmitter one can send x1 through xn in n channel uses. Transmitter 2 sends x2 of 1 through x2 of n in n channel uses, and each xin, these are real vectors, all right, and the output of the channel yn is equal to h1 x1n plus h2 x2n plus zn, right, where h1 and h2 are some real constants. You can think of these as attenuation coefficients, and these are assumed to be known by all. So we assume that even before the actual transmission happens, you have already estimated these channel coefficients. Right? So the channel coefficients h1 and h2 are known. h2 known, and Zn is assumed to have IID components, Gaussian with mean 0 and variance sigma square, and we assume that sigma square is of course known. Right? So this completely specifies the channel. In addition, you have the following input constraints or cost constraints, cost power constraints. Right? So So we want to have x1 n square should be less than or equal to the 2 norm of x1 n the whole square should be less than or equal to n times p1, where p1 is sort of the power constraint, and x2 n 2 norm squared should be less than or equal to n times p2, where these p1 and p2 are of course given beforehand, right? So these are the constraints that need to be satisfied. And for this particular channel, let us try to find out what the capacity region is. Okay. So the capacity region, of course, is given by, again, just by extending the case from the discrete case to the continuous case using discretization. We can say that the capacity region is the following. So it is the set of all R1, R2 satisfying R1 is less than or equal to the mutual information between X1, Y given X2, Q, R2 less than or equal to the mutual information between X2, Y given X1, Q, and R1 plus R2 less than or equal to the mutual information between X1, X2, and Y given Q. Right, and we look at this over all possible densities fx1, fx2, sorry, x1 given q, f x2 given q, pq, where q can be taken to be binary. But note that we have to satisfy a power constraint. So you look at only those densities which satisfy expectation over x1 of x1 square less than or equal to p1, expectation x2 square is less than or equal to p2. Right? So these are the constraints. Now, instead of looking at this particular channel, okay, anyway, doesn't matter. So okay. So this is the capacity region. Right? Now let us see if we can simplify this in any form. Right? And we'll also see we'll see some techniques which are commonly used and see what rates can be achieved using those particular techniques. Okay, but first let us try to evaluate some of these quantities, some of these mutual information quantities. Right, so let's try to find the mutual information between let's say x1, y. All right. So throughout we'll assume that we'll first fix a distribution which satisfies these conditions. So can someone tell me, can someone give me an example of a distribution which satisfies these two constraints? What is the most natural thing that you would think of?
Sir, can you repeat the question?
Okay, so right now we need a candidate distribution, right? So we want to evaluate these mutual information quantities, and ideally we want to choose the distributions fx1, fx2, and so on, such that the capacity or the region that we have, the region described by this by these three inequalities, is as large as possible. All right. So what is the first thing that you would start with? You want these densities fx1 given q, fx2 given q, to satisfy that the variance is less than or equal to p1, or second moment is less than or equal to p1, and the second moment of x2 is less than or equal to P2. All right. So since this is a Gaussian channel, what is the first distributions for x1 and x2 that you would think of? Right? Which one do you think would give the best rates? Which distributions do you think would give the best rates? Yes, anybody?
Sir, Gaussian with zero mean and
Yeah,
some
so
distribution.
Gaussian. So what would be the mean and variance? So zero mean and then?
Variance we can take sigma square.
So you
This
want to
is equal
satisfy
to
these
P1.
power constraints, right? So yeah, so we'll
Sure,
take
sure.
fx1 to be Gaussian with mean 0 and variance
Variance of
p1,
P1, sir.
and fx2 to be Gaussian with mean 0 and variance p2. Okay, that's fine. So let's maybe evaluate some of these terms. Okay, what would happen to the mutual information between x1, y given x2? So what is this equal to? This is the differential entropy of y given x2 minus the differential entropy of y given x1 and x2. Okay, so if x1 and x2 are ID Gaussians, then y, which is equal to hx1 plus hx2 plus z, is also going to be Gaussian, right? And what can you say about y? What is going to be the mean and variance of y?
Sir, mean will be 0 and
Okay, and what about the variance?
this will be some P1 plus P2.
Are you sure? So
Sigma
remember,
So
this is the channel, right?
sigma square plus P1 plus P2.
Again, careful, look at the channel.
Settle.
So x1 is Gaussian with mean 0 and variance p1. x2 is Gaussian with mean 0 and variance p2. So y is going to be Gaussian, but what is going to be the variance?
P1 plus P2 plus sigma square, right, sir? Wouldn't it be?
No. The channel is h1 x1 plus
sir, with
h2
coefficient
x2.
means we can just do under
So
sir, with channel coefficient H1, this will come H1
correct. The
sigma
channel
square 1
coefficient should appear, but so
is
what will it be?
square root of H1 sigma square 1 plus sigma H2
Why
is.
do you get square root?
If we are
Uh-huh.
taking only net sigma, sir, if sigma square, then only H1 plus sigma is, this will be sum of that.
X2 plus z, they're all independent.
Yes, sir.
So
H1 P1
variance of y will be equal to variance of h1 x1 plus
H2
variance
variance
of h2 x2 plus variance of z. But what is the variance of h1 x1 equal to?
P1 and the H1 will be come outside. No?
So is variance of h1 x1 equal to h1 times the variance of x1?
H1
Sir,
square.
H1 is square. Sir.
H1
Ah.
square times.
Yes,
H1 is
so it's
square.
h1 square times the variance of x1, which is p1, plus h2 square times the variance of x2, which is p2, plus the variance of z2, which is sigma square. Right, so y is Gaussian with mean 0, and the variance is h1 square p1 plus h2 square p2 plus sigma square. Okay, so given x2, what is the entropy of y equal to, or the differential entropy of y equal to? So this is equal to, so y equal to h1 x1 plus h2 x2 plus z. So this is the differential entropy of y given x2. Can someone tell me what that would be equal to in terms of x1 x2 z? So here's a hint. So if you have h of x plus y given, say, maybe x bar plus y bar given y bar, what is this equal to? And x and y are independent of each other. This is equal to h of x bar, right?
Yes.
Right. So using this, what can you say about h of y given x2? So you also know h1 and h2, right? These coefficients h1 and h2. So what is the differential entropy of y given x2 equal to?
Entropy of x1
So
z
h1
plus
x1
z
plus z.
z.
Right. Okay. So
Yes.
good. So now what about h of y given x1 x2?
H of z on.
Correct. So it's just entropy of the differential entropy of set. Okay. So now, what is the differential entropy of h1 x1 plus z?
Half log that, I mean, for the Gaussian the same formula, and we have to
Correct.
just vary the variance.
Half log 2 pi e times, what is the variance of h1 x1 plus z?
So h1 square p1 plus sigma square.
p1 plus sigma square. Okay, that's good. Minus h of z, which is half log 2 pi e sigma square. Right, so this is basically half log. So 2 pi e times h1 square p1 plus sigma square divided by 2 pi e sigma square. So the 2 pi e gets cancelled, and this just reduces to half log 1 plus h1 square p1 by sigma square. Right, so this is the mutual information between x1 y and x2. Right, so similarly, again, if you choose them to be Gaussian, then the mutual information between x2 and y given x1, this just by replacing x1 and x2, and therefore replacing p1 and p2, you get that this is half log 1 plus h2 square p2 divided by sigma square. All right, and what is the mutual information between x1, x2, and y? This is h of y minus h of y given x1, x2. What is h of y equal to? Times
h1 square p1 plus h2 square p2
h2
plus
square p2 plus sigma
plus
square. Right, and what is h of y given x1, x2?
just
So
sigma square.
Yes,
the sigma square.
just sigma square.
Yes.
Right, so this will just evaluate to half log 1 plus h1 square p1 plus h2 square p2 whole divided by sigma square. Right, so the sum rate should be less than or equal to this, and the individual rates should be less than or equal to these. Right, uh, so once again, let's also evaluate the following quantities: I of x1 y and I of x2 y. Y given x1, right? So this is equal to, the first term as we've seen is half log 2 pi e times h1 square p1 plus h2 square p2 plus sigma square minus h of y given x1 as we've seen is half log of 2 pi e. So h of y given x1 is the same as h of h2y plus z. Sorry, h2 x2 plus z. So this is h2 square p2 plus sigma square, which is half log of h1 square p1 plus h2 square p2 plus sigma square divided by h2 square p2 plus sigma square, which is nothing but half log 1 plus h1 square p1 divided by h2 square p2 plus sigma square. Right, and similarly, I of x2 y, this is equal to half log 1 plus h2 square p2 divided by h1 square p1 plus sigma square. Okay, so let's compare all of these with the capacity of the AWGN channel, right? So let us call C of p comma sigma square to be half log 1 plus p by sigma square. So this is the capacity of the point-to-point AWGN channel with input power constraint of p and noise variance sigma square. Okay, let us see what each of these terms evaluate to. Right. So first we started with this conditional mutual information term. So let's just look at this one. Right. So what is this equal to? This is the same as, or this term is the same as the capacity of an AWGN channel with input power constraint h2 square p2 and variance and noise variance sigma square. right? And whereas this, the sum rate, is less than or equal to the capacity of a point-to-point AWGN channel with power constraint H1 square P1 plus H2 square P2 and noise variance sigma square. Right? But perhaps these two terms are a little more interesting. So this is the capacity of the AWGN channel with input power constraint H1 square P1. But the noise variance now is not just sigma square, it is H2 square P2 plus sigma square. So effectively what this is this would be the same as the capacity of the AWGN channel, but when you're treating, so this is the capacity for the of the AWGN channel when you want to decode X1, but you're treating X2 as noise, right? So that is why the noise, the effective noise variance is H2 square P2 plus sigma square, right? And similarly here, the mutual information between X2 and Y turns out to be C of H2 square P2, but the effective noise variance is H1 square P1 plus sigma square. All right. So if we try to draw the effective or the achievable rate region for these distributions, this gives us a pentagon, as we've seen a number of times. And the pentagon is as follows. Black. Okay, so we've seen two things. One is, see, oops. C of H1 square P1 sigma square, which is basically the mutual information between X1, Y given X2. This is R1, this is R2, and let's say that this is C of H2 square P2 comma sigma square. All right, so but then we have two other quantities, the mutual information terms, which are C of H1 square P1, but the noise variance is H2 square P2 plus sigma square, and maybe this is again I of X2Y, which is C of H2 square P2 comma H1 square P1 plus sigma square, right? So the corresponding pentagon would look something like this. So we have all the way over here. This goes from here to here. Right. So this is what the pentagon would look like corresponding to this particular distribution. In fact, for the special case of the AWGN channel, for the Gaussian MAC, the pentagon is optimal. So in fact, this is the capacity region. So the capacity region is a pentagon in the case of the two-user Gaussian MAC. For a general MAC, for a general discrete memoryless multiple access channel, the pentagon is not really the optimal rate region. It's going to look a little more curved. Right, and we'll shortly see another example where maybe that is not the case. But at least for the Gaussian MAC, this is the capacity region. All right. So, and this, as we know, is achievable using successive cancellation decoding and time sharing. Right. Okay. So this is one approach, and this is the optimal approach. So let's also look at a couple of suboptimal approaches. So suppose we did TDMA, right? So this is optimal. So this is optimal, right? So successive cancellation decoding plus time sharing. But now maybe let's look at something else. So suppose we used TDMA. Then what would be the achievable rate region? So in TDMA, one user would operate at its capacity, whereas the other user would remain completely silent. Whereas in the remaining fraction of the time, the other user would be completely active, whereas the first user would be completely silent.
Line joining C H2 square P2 comma sigma square and C H1 square P comma sigma square.
Exactly. So it would be just the line joining these points. Right. So this point is achievable when user 2 is active all the time. This point is achievable when user 1 is active all the time, but user 2 is always silent. And any point in between or any point on the line joining these two is achievable when when only user 1 is active for some fraction of the time, and the remaining fraction of the time user 2 is active. Right. So this gives you one more rate, one more set of rates. Okay. All right. So that is the second approach. So let's look at another approach. Right. So let's see the case when you treat the other user as noise. Right. So by this I mean that both users transmit simultaneously. Okay, they send their code words, but then you decode the two messages independently. So to decode user one's message, you treat user two's message as a noise, and you treat user two's code word as part of the noise. And to decode user two's code word, you treat user one's code word as part of noise. Okay, so what rate is achievable? So what R1 would be? So to decode, oh, as noise. So basically each user uses a single, just a codebook designed for the point-to-point AWGN channel. Each user uses codebook designed for AWGN channels. So to decode X1N, the decoder treats X2N as part of noise. And to decode the second user's code word, you treat X1N as part of noise. Right, so basically you have Yn equal to H1 square, sorry, H1 X1 plus H2 X2 plus Z, and basically this is going to be the noise. Right? So you treat this as though it's AWGN and then try to decode X1 from Yn. Right? So what rate is achievable for this if you want to do it?
Half log. Okay, 0 comma.
No. So the rate, right? It's basically the capacity. So it's effectively an AWGN channel where the power constraint is of course
H1 square P, comma, H2 square P2 plus sigma square.
Correct. H2 square P2 plus sigma square. And similarly for decoding X2, so the probability of error is vanishing as long as R2 is less than or equal to C of H2 square P2, and where the noise is effectively H1 square P1 plus sigma square. Right, and that basically corresponds to these 2 points over here. So as long as R1 is less than this, decoding can be done. As long as R2 is less than this, decoding can be done. Right. So what does the achievable rate region look like? What shape will it have?
So line joining those 2 points.
Think about it carefully. So R1 should be less than or equal to this, and R2 should be less than or equal. So R1 should be less than this. Okay. So anything to the left of this is this, and everything below this.
Rectangular.
Exactly. So it's going to be a rectangle. Right, and this is basically treating the user as noise. Okay, that's fine. So, but maybe we can do there's something else in between. So we've seen sort of 2 schemes, 2 suboptimal schemes, right? We could of course do successive cancellation decoding, but there are sometimes merits to looking at more simple coding schemes, right? So the question is, can you do something a little more sophisticated than TDMA, but slightly better than, but of course something better than this, but maybe not as good as successive cancellation decoding. So among all of these, treating the other user as noise is clearly, it is suboptimal. It is the worst possible technique you can use. All right, so that's something that we all agree on. So now let's see if we can do something even better than plain TDMA. And that is what I call TDMA with power control. Okay, and the TDMA with power control approach is the following. So note that what did we do in TDMA? We decided that for alpha fraction of the time, user 1, so for alpha n channel uses, user 1 transmits, so this is plain TDMA. So for alpha n channel uses, user 1 transmits at a rate C of H1 square P1 sigma square, whereas user 2 is silent. And user 2 basically transmits 0, right? And for the remaining 1 minus alpha n channel uses, user 2 transmits at a rate C of H2 square at a rate R2 equal to C of H2 square P2 comma sigma square, whereas user 1 is silent or basically transmits zeros, right? But this, maybe this can be improved slightly. We're not making use of all the resources in this particular plain version of TDMA. Can someone tell me why? So is there some resource that you're not utilizing fully in just TDMA?
Channel?
No, so the channel is being used by at least one person at all times, right? So that is being used fully. Is there some other resource which is not being fully utilized? So what about the power? How much power is in plain TDMA? How much power is user 1 using?
P1.
Are you sure that so by that I mean what is norm
As per current,
x1?
in our assumption, we have taken P1, right, sir?
No, that is the power constraint, right? So you have to satisfy the power constraint. But how much power is actually being used by user 1? So note that user 1 is transmitting at a rate h1 square square p1 comma sigma square, but he's using it only for alpha and fraction of the time. Right? Right? So basically this is only equal to, so you're using it only for alpha n fraction of the time. So the amount of energy used is in fact just alpha n times p1, correct?
Sir, but we have n point p1 on this constraint.
Exactly. So, but the constraint is n times p1. So
Yes.
you're using less power than you actually have. You
Yes.
have a budget of p1, but you're using only alpha p1 of it because you're remaining silent for the remaining 1 minus alpha fraction of the time. And similarly, x2 n square is 1 minus alpha times n times P2, right? So this is for user 2. So you're not making full utilization of all the resources. So the power is underutilized. Right? So and obviously we can do better. So one obvious way of improving this is that's what I call TDMA with power control. So TDMA with power control. You basically just pump in more power for those alpha n fraction uses. So user 1 basically transmits at power P1 by alpha for alpha n channel uses. And user 2 again will do something similar, so it will transmit at power P2 by 1 minus alpha for 1 minus alpha n channel uses, whereas the other user is again it's TDMA in the sense that user 1 is going to, when user 1 talks, user 2 remains silent. When user 2 talks, user 1 will remain silent, right? So you have alpha n channel uses. So you have alpha n channel uses, and you will split this into two parts. Alpha n, it's called a 0. So in this duration, user 1 is active at power P1 by alpha, and the rate at which he will now transmit is basically going to be alpha times C of H1. So the rate will be H1 square P1 by alpha, and the noise variance, of course, is going to be sigma square. And user 2 is silent. And in the remaining 1 minus alpha fraction of the time, user 2 will be active, and he's going to transmit using power P2 by 1 minus alpha, and the rate is basically going to be 1 minus alpha. The effective rate is going to actually be transmitting at a rate C of H2 square P, P2 by alpha, by 1 minus alpha, sigma square, sigma square. Right? And user 1 is going to remain silent. Okay, so this is of course TDMA with power control, and it performs much better than plain TDMA. The rate, of course, is a little more the set of rates that this satisfies is a little more complicated. It's not a straight line anymore. So what you get is so let's call this TDMA with power control, and this is going to look something like this. It's going to be some convex region, and this is roughly what it would look like. Okay, I don't have a good picture to show you, but this is what so it will do strictly better than TDMA, but it's also going to be worse than successive cancellation decoding and time sharing. Right? So TDMA with power control is something much easier to implement. You don't have to do any sort of successive cancellation decoding. You just use plain single user codebook. Only one user is going to talk at all the time, whereas the other user is going to remain silent. So that's simple, and it's obviously better than plain TDMA, right? And it's obviously, of course, it's much better than treating the other user as noise, right? So one thing to note, especially when you're talking about successive cancellation decoding, is that we have assumed that when we were deriving the rates, when we were doing these random coding arguments, when doing successive cancellation decoding, you treat the other users for decoding the first user's message, you treat the second user's message as noise, as part of the noise, right? Now, you could use a single user codebook for this as well, but the single user codebook would work well only if the noise is Gaussian, right? But in fact, the channel that you have when decoding, say, the first user's message is H1 X1 plus H2 X2 plus Z, right? And this is not Gaussian, right? In practice, when you're using an actual code book, when you're not doing some kind of random coding argument, when you're using one specific code, let's say an LDPC code or some kind of or some constellation, Z is Gaussian, but X2 is not Gaussian, right? Because it's coming from some finite set. It's some set of code words. So this quantity is not Gaussian. So if you use a code book designed for an AWGN channel and you try to do plain successive cancellation decoding, this is not going to work well in practice, right? And that is why you need to design slightly better codes which work even in the case where you're trying to decode X1 from H1 X1 plus H2 X2 plus Z. Right, and that is why successive cancellation decoding is more complicated than plain TDMA, right? Because you need to design better code books. So a code book that works for the AWGN channel does not necessarily work for this particular channel. All right, but an easy way to improve upon TDMA is just do TDMA with power control. You just make you're wasting power in the remaining alpha n channel use. It's going unutilized. So use that additional power in the time you're talking. Right? Just speak more loudly in the duration that you're actually talking, and that does pretty well. Right? Any questions? Okay, so let's stop at this point. We'll continue with another example. We'll see maybe we'll see a slightly more complicated example and work out some numerics. So this was a simple case. The Gaussian case is very nice because you know what the best distribution is in some sense, and the capacity region is a pentagon. So next time maybe we'll see an example where the actual capacity region is more complicated. It can't be described by a single pentagon anymore. All right. So okay, so let's stop at this point. See you all next week.